All right, it looks like we're live on YouTube. Hello, everyone. Welcome to this session on secure multi-party computation. This is the second of 3 sessions. I'll be one of the session chairs along with Antigone. You'll see her as well. But we'll just get started with the first talk. As usual, 5 minutes for the talk and 5 minutes for questions afterwards. So the first talk is always have a backup plan, fully secure synchronous MPC with asynchronous fallback. And Chenda is going to give the talk. So whenever you're ready, take it away.
Yeah. So can you see my screen?
Yes.
Okay. Okay, so thanks for the introduction. My name is Chenda. I'm from ETH Zurich. I'm gonna talk about, as you said, about synchronous MPC with asynchronous fallback. And this is joint work with Erika and Julian from University of Maryland. So the setting is that of secure multi-party computation, where parties want to jointly compute a function over private inputs without revealing anything about the inputs, just as if they had a trusted party available. So very roughly, MPC protocols can be classified according to the underlying communication model. And perhaps the most popular one is the synchronous model. This assumes that parties have access to synchronized clocks, and everyone knows an upper bound on the network communication delay. While having these assumptions is very convenient, in many settings, this may not be completely realistic. For example, if the network delay is unpredictable. A much more realistic model is the asynchronous model. So here, protocols do not make any assumption on the synchrony of the clocks. They only use the fact that messages sent are eventually delivered. So then one can ask, okay, then why do we care about synchronous protocols, right? And perhaps one reason is that having such strong assumptions allows us to have also very strong security guarantees. So synchronous protocols tolerate a high threshold tolerance, so up to n-half, and parties compute exactly the output that one would expect. And on the other hand, asynchronous protocols only get up to n-third corruptions, and unavoidably, the inputs of up to t parties are ignored. This means that parties do not really get f on the inputs, which would be the normal output, but the adversary is allowed to choose up to t inputs and substitute them by a default value bottom. So in view of this, we can ask whether there is one single MPC protocol that achieves guarantees in both regimes. And we would like to have like high threshold tolerance when the network is synchronous, of course, with input completeness. But even when the network is asynchronous, we would like to still be able to tolerate a reasonable amount of corruptions, but of course, allowing some of the inputs to be ignored. And this is the question that we answer in this work. We say that, yes, such an MPC exists if and only if TA plus 2TS smaller than n, and the number of ignored inputs is at least TS in the asynchronous case. So here is some related work. There are some nice recent works by Blomkatz and Loss that study such questions for the case of agreement primitives, first for Byzantine agreement, and then for state machine replication. And there are also some asynchronous MPC protocols out there. I believe this was the first one by Hirt et al. that achieve input completeness when the network is synchronous. So let's get an overview of our construction. So what we do is we rely on a core primitive, which is basically we enhance a synchronous MPC protocol that not only gives all the guarantees that we would like to have when the network is synchronous, but also achieves reasonable guarantees when the network is asynchronous, meaning that every party gets an asynchronous output, which is allowed to ignore a bunch of inputs, or everyone obtains bottom. And the way we achieve this is following the CDN approach, Kramer, Damgard, and Nielsen, which is based on threshold homomorphic encryption. And once we have such a primitive, it's easy to guess how to get the MPC that we want. We first run the synchronous enhanced MPC protocol, and if the output is bottom, we run the asynchronous, any asynchronous MPC protocol. And why does this work? Because if the network is synchronous, we inherit the security guarantees from the first component. But even if the network is asynchronous, either everyone obtains a YA output, so we're happy, or everyone obtains bottom, in which case it's completely safe to execute the asynchronous fallback. So for more information, I refer you to the full video presentation and or the full version of the paper. Thank you.
Sorry,
You are muted.
Yeah, I was on mute. So thanks a lot, Genta. So if you have any questions, please paste them either here on Zulip. I think there's already a question on Zulip from Karsten. How much overhead does the compilation of the synchronous protocol to have this extra property cost in terms of computation or communication?
So we have a bit more communication. So in fact, I might have some slides here. Let me see. But I would say compared to CDN, not that much. So basically what we do is instead of broadcasting, we do right. We run an extra ACS protocol, and this will incur basically some communication complexity because this is N broadcast and N BA protocols also. Yeah. But apart from that, no. Yeah.
Okay. Yeah, I don't see more questions. So just a quick question. So your the primitive that you're using all the way is the homomorphic encryption?
The primitive that we rely on is additively homomorphic encryption, threshold
That's
additively
okay.
homomorphic encryption. Yeah, it's not fully homomorphic.
Okay, thanks a lot for your time. So if you have more questions, please feel free to ask Genda offline.
Mm-hmm.
Now we can move to the next talk.
Thank you.
So the next talk is about stacked garbling, garbled circuits proportional to longest execution path, from David Heath and Vlad Kolesnikov. And David is giving the talk. So David, you can start.
Thank you. Can you hear me and see my slides?
Yes.
Okay. Yeah, so I'm David Heath, and I'll be presenting stacked garbling. Again, this is joint work with my advisor, Vlad Kolesnikov. So this work is about garbled circuits. So I'd like to briefly review the technique. So garbled circuits is a protocol between two players, a so-called circuit generator and evaluator. And the circuit generator's job is to build an encryption of a function represented as a circuit. And in this case, we'll have her do so starting from a pseudo-random seed. So she builds this encryption, what I'm denoting M. M is for what we refer to as the material. And the material contains a collection of encrypted truth tables encoding the semantics of the individual gates in the Boolean circuit C. Now, after having constructed M, the generator sends M across the network to evaluator. And the key point is that this simple sending of material from the generator to evaluator is the single most expensive part of garbled circuits, and it is this cost that we decrease in this work. So the evaluator now has the material M, and he also obtains so-called input labels, though I won't describe how he gets these, but these are encryptions of the logical inputs to this circuit. The input labels in the material are sufficient information for the evaluator to step through this circuit gate by gate and eventually arrive at labels that encode the circuit output. Now the two players can communicate in order to jointly decrypt the circuit output. So this is garbled circuits, and in this work, we extend garbled circuits to efficiently handle conditional branching that arises in the underlying program. So for example, this if-else program that I have written here. In order to represent conditional programs, we need more than one circuit. In particular, we need one circuit per branch. So we'll consider these two circuits C1 and C2, and I'd like for you to imagine the case where the circuit C1 is taken during the evaluation of this conditional branch. The key point is that the circuit generator and evaluator should not know which of these two branches are taken during evaluation. And our approach is going to reduce the amount of information needed to represent the the encryption of a conditional branch without having to disclose to any of the players which branch is taken. So our approach is as follows. First, instead of having only one seed, we have one seed per branch. So the circuit generator constructs encryptions of each of the branches in the conditional to get, in this case, strings M1 and M2. Now, the key point is that instead of sending M1 and M2 separately, as would normally be done, we instead send their bitwise XOR, M1 plus M2, which is of course shorter than sending the two strings separately. So this bitwise XOR is the source of our improvement. The evaluator now has access to this XOR, M1 plus M2, and he also gains access to the seed that encrypts the non-taken branch, though I won't explain how this is conveyed. Now, if we assume that the evaluator somehow did know which branch was taken, then it would be relatively straightforward to see what he has to do, because he can use this seed, S2, to re-encrypt the non-taken branch and calculate M2. Given these two pieces of material, he can use bitwise XOR to extract the material for the taken branch and then evaluate as normal. Of course, the key problem is that the evaluator is not supposed to know which branch is taken. In our approach, we resolve this by having the evaluator symmetrically attempt to evaluate both branches. By this, I mean that completely symmetrically, the evaluator uses the same seed to also encrypt the first circuit. This does not yield material M1, but instead yields a new string M1 star, different than the encryption built by the generator. Therefore, when the evaluator attempts to extract the material M2 by bitwise XORing, he is unsuccessful. And when he evaluates, he does not arrive at valid output labels, but instead arrives at random looking garbage that is neither an encryption of 0 nor of 1. Now, if we could somehow eliminate this garbage non-interactively, then we would have evaluated this conditional very efficiently. To do this garbage collection, eliminate the garbage and propagate the valid labels, we add a few components. First, we add a demultiplexer. The demultiplexer's job is to handle inputs. Onto the taken branch, it propagates valid inputs such that C1 evaluates as normal. But on the non-taken branch, it places fixed garbage input keys that are independent of the circuit input. Thus, when the evaluator runs this circuit under encryption, he still arrives at garbage labels, but these labels are fixed. Our final observation is that the generator can place herself in the shoes of the evaluator to pre-compute these garbage output labels. That is, she can pre-compute these pink keys. Knowing the pink keys and knowing the valid output labels is sufficient information to build a new encrypted truth table, which will obliviously collect garbage. So put together, stacked garbling allows us to bitwise XOR the material from different conditional branches. We add additional circuit gadgets that allow us to collect garbage. Put together, stacked garbling offers a theoretical improvement to garbled circuits' ability to handle conditional branches. So thank you, and I'll take any questions.
All right, thanks, David. That's some exciting work. If anyone has any questions, feel free to ask in either Zulip or here on Zoom, and we'll get those relayed to the speaker. In the meantime, you know, the very last thing you said is this is a theoretical improvement. Is it also a practical improvement?
Yes, so I'll refer you to our paper on ePrint, but we implemented this, and I should emphasize that there is actually a computation overhead to doing this trick, in particular where the generator has to pre-compute this garbage. So we increase the amount of computation needed compared to standard garbled circuits, but we show that depending on your hardware and for most slower networks, it's very much well worth it to make this trade-off. And the communication improvement is worth it, basically. So yes, it's practically more efficient for most cases.
Okay, excellent. Marcel is asking on Zulip, is the number of interaction rounds independent of the number of branches in the circuit?
That's right. So this maintains the constant round property of garbled circuits. So there are no added rounds of communication.
And I suppose you can nest this little gadget that you saw that you're showing on the screen, you can nest it inside?
Yes. So in our paper, we show two constructions. We show how to nest it, and then we also show how to sort of vectorize this. So you can imagine the demultiplexer feeding inputs to not 2 circuits, but to 10, which turns out to be computationally more efficient by a small amount.
Okay, great.
So both of these are possible.
Great. We still have time if there are more questions. Otherwise, I can keep asking questions all day. One of my questions was, this seems to work really well when there's a conditional branch in the circuit, but is there any hope of applying tricks like this for circuits that you don't really naturally write in terms of switching statements? Like, for example, the AES circuit. Is there a way to apply your kind of ideas to maybe an unnatural example of a circuit?
Yeah, I'm not sure. So the key property that you need is that there does need to be some sort of exclusive behavior, because as you can see on the slide here, we're giving up the ability to correctly evaluate the circuit C2. So if there is not some part of your circuit which in the end is not going to be evaluated, I don't see how you can apply this technique. That said, if it's not written in a high-level language, perhaps there are ways to kind of extract, like by some compiler techniques, deduce which parts of the circuit are exclusive with one another. But if in terms of like AES, it seems like a stretch, because I think you need the output of all of the gates in order to compute the eventual output.
Okay, excellent. Looks like more questions are appearing here. We'll try to get to them quickly if we can online. Frank Davis is asking, you're trading off providing M1 and M2 as well as the seed because you send the XOR. If the XOR value in the seed is the XOR value and the seed shorter, then simply giving M1 and M2 separately.
Yes, so the seed is very short. You should think of the seed as 128 bits or something, whereas the M1 and M2 are proportional to the number of, well, in truth, proportional to the number of multiplicative gates in the circuit times the security parameter. So the material is much, much longer than the seeds. And in fact, we show that in our paper, we don't even use additional seeds. We just there's a wire which is encoding which branch is taken, and we just use that wire to perform the encryption. We use that as the seed. So the seed sort of comes completely for free. It's just the material that costs anything.
Okay, and maybe one last question, because we're running out of time. I think this one has a short answer. Pratik is asking, what is the assumption on the underlying garbling scheme, the underlying encryption for the garbled gates? Right,
so we use the underlying garbling scheme we formalize has to be so-called stackable. And what this means basically is that the encryption and the labels are indistinguishable from a random string. So that's sort of the formal constraint. And you can there's a few other things, but you can read that in our paper. But that's the main one, is that the stuff that comes out of the circuit has to look random, basically.
Okay, thank you for surviving the barrage of questions. There's one more question I see in the Zoom chat. Maybe you can handle that offline.
Absolutely.
But I think it's time to move along. The next talk is on better concrete security for half-gates garbling in the multi-instance setting. I think Chen Kai is going to give the talk, so whenever you're ready, please go ahead and share your screen.
Yeah, thank you.
Yeah, looks good.
Hello, I'm Chen Kai. I'm presenting our paper, The Better Concrete Security for Half-Gates Garbling in the Multi-Instance Setting. In this paper, we mainly study the concrete security for half-gates garbling. And first, we gave an attack on the current half-gates implementation. To note that it doesn't mean that half-gates protocol is insecure, but we do find a weakness when the hash functions in the half-gates is not instantiated properly. And also, there is a problem in some previous papers where there's a lack of concrete security. Normally, they only provide the asymptotic security bound. And also, we gave a new abstraction of hash function, which can give a better concrete security. And first, let me review the Yaws-Garble circuits. The Yaws-Garble circuits is a two-party computation protocol. It allows two parties to jointly compute function without revealing anything beyond the output. And it usually represents a function as a Boolean circuit with AND and XOR gates. And the half-gates protocol is a state-of-the-art garbling scheme. It's compatible with most other optimizations for the garble circuits, and it can efficiently compute the AND gate with minimal communication. And it also uses fixed key AES-based garbling. It means that it instantiates the hash functions in the garble table using the fixed key AES. And the thing is that when this hash function is modeled as a random oracle, there's a tight security reduction. But when we instantiate this using the fixed key AES, then there is a gap to exploit. And I'll skip the details of the attack and give the results of our implementation. Here in our analysis, the attacker succeeds in running time to the K over C. Here the K is the B length of the label and the C is the number of AND gates in the circuit. And this attack also applies for the multi-instance setting, where the adversary may receive multiple circuits which are independently garbled. And this C can be the total number of AND gates in all these circuits. And the results show that even if you use KB label for the garbled circuits, it doesn't mean you have KB security. For example, if you use ATB label with a circuit size of 2 to the 40, then this circuit can be completely broken. And this attack also applies for the skins who use half-gates garbling, and including some works may present in this conference. And following our results, we estimate that we can break the circuit using ATB label and the circuit size 2 to the 30 in 267 machine months. If we run this attack in the cloud, we estimate it'll only cost $3,500. And this attack is highly parallelable. So if we instantiate many machines, we can run it simultaneously and finish this attack in a short time. So how do we fix this problem? Now we already have the half-gates protocol, and the first step is to design a new abstraction which models the use of the hash function in the half-gates protocol. Then, in the sense of this abstraction, we design a new hash function which satisfies all the security requirements from this abstraction and provide a better concrete security. Here are our results of the design. In the abstraction layer, we design the multi-instance trackable circular correlation robust hash function. It takes the inputs, the input label, a tweak I and the random bit, and outputs the linear combination of the hash value and the global delta. Because we consider multi-instances, so here the adversary can receive U instances, and this tweak I can be reused for almost mil times. And in the sense of this abstraction, we design the hash function MMOE. It takes the inputs, the label X and the tweak I. Here, the sigma X is a linear isomorphism. It's a kind of permutation. And this E is modeled as an ideal cipher. The key of this ideal cipher is this tweak I. To further bound the maximum reuse of a single tweak, we start this I from a random point. To know that in previous fixed key AES-based implementations, they use a gate identifier I, and it always starts from 1. Here we start it from a random point. And after embedding all these designs in the half-gate garbling, we can derive a new concrete security bound. And here are the implementations of our hash function. We make use of the hardware support and some pre-compiled instructions to accelerate these operations, including the AES at 128, the linear isomorphism, and the batched key scheduling. And the table shows the performance of our implementation. In most of the situations, when the network bandwidth is less than 2 gigabytes per second, the network is still the bottleneck. So the performance is the same as the previous implementation. When the network resource is enough, our implementation is just 35% slower than before. And we further optimized this after we published the paper, and now they're almost the same. So in summary, we enhance the security and make little compromise on the efficiency. The implementations have been in the EMP toolkit library. There's also a link to the full version of the paper. Thank you.
Thanks a lot, Zenkai. Okay, so there's a question from Mike, but before, actually, can you give an intuition of the attack?
So sorry.
Can you give an intuition of the attack and why you had to change to that hash function?
Yeah, because we have showed an explicit attack on the current half-gates implementation. I have mentioned that in the previous works, they only provide the asymptotic security, and it's that asymptotic security bound is not enough for instruction to use in the practice. That means when the circuit size is too large, then this circuit can be completely broken. So I think the motivation is that we have given an explicit attack, which can be implemented in the real world practice. So that can serve as a motivation of this work, I think. So there's a need to provide a new hash function, which is more secure and more suitable to use the fixed key AES as a to design a hash function based on the fixed key AES.
Okay, yeah, I was just asking why you had to like move to that hash function, but we can I can ask you more details afterwards. In the meantime, Mike, can you just ask your question online?
Sure. You had an attack that the cost was 2 to the k divided by c, and c is the total size of the circuit. Does it have to be a single circuit, or does it also work across many circuits? Because in half gates, different circuits would have a different correlation, a different pre-XOR delta value. Does it still work in that case?
It works for multi-instance setting when adversary receives multiple circuits, even if they are garbled independently using different global correlations. This attack can still apply, and the important thing is that it's increase the chance that the attacker break one of the circuit. I mean, at one time when the attacker find a hit, like the pre-image of the hash, it can still only attack one of the break one of the circuit, not all of them. But all of them can increase the chance for the attacker to break one of them.
Thanks.
Okay, thanks a lot, Zenkai. There are no more questions, and actually we're right on time to move to the next talk. Thanks a lot.
Thank you.
So next we have Rahul, who is going to talk to us about improved primitives for MPC over fixed arithmetic binary circuits. We join work with Daniel Escudero, Satrajit Ghosh, Marcel Keller, and Peter Scholl. So yeah, Rahul, whenever you are ready, you can start.
Okay, thanks for the introduction. So this is going to be a quick overview about our work, improved primitives for MPC over mixed circuits. So as we know, in MPC, we have two computational domains, arithmetic and binary. Arithmetic does well for operations like multiplications, and the binary domain does well for operations like comparisons. Given that multiplications and comparisons are interleaved in applications like biometric matching and machine learning, we have motivation to have efficient protocols that allow us to switch back and forth between the two domains. Works like ABY, ABY3, etc. have made progress in this direction by proposing frameworks that let us do this, but they're usually either in the weaker honest majority setting or in the semi-honest corruption setting. The recent work of Dabitz works in the dishonest majority setting with active security. Taking inspiration from them, we propose a framework which works in both the settings, but outperforms Dabitz in the dishonest majority setting. So these are our results at a high level. We introduce a new cryptographic object called EDA-bits. EDA-bits can be used to do conversions in MPC. We have improvements to truncation and secure comparison protocols. And although we support all corruption thresholds, we observe the most gain in the dishonest majority setting with active security. So to generate EDA-bits, we propose a novel cut and choose protocol, which might be of independent interest. It works by exploiting tamper resilience properties of binary circuits. And finally, we implement all our constructions and some end-to-end applications, benchmarks for which are available in the paper. What I'd like to point out is that if we consider comparisons, we use up to 25 times less communication, and we have up to 47 times higher throughput than previous state of the art, which is debits. So an ERA bit is an extended debit. It consists of m random bits, which are shared over F2, and their corresponding value shared over Zm, where m is either a prime order field or a ring. So to generate ERA bits were generated incrementally with debits, where we first batch produce a large number of debits and combine them to make an ERA bit. Our approach was to instead generate ERA bits directly. And the advantage of doing so is that we can use cheap OT-based multiplications over F2 instead of more expensive homomorphic encryption-based multiplications. As a result of this, if we consider the active security case with 2 parties, we are up to 3 to 4 times faster than debits. So this is how we generate ERA bits at a high level. Each party secret shares a set of ERA bits. We run a cut and choose protocol on each of these sets. What we get as a result is verified private ERA bits, but we can't use them directly because the party that proposes the set also knows the underlying values. So we take one ERA bit from each party and we add them using a binary circuit. At the end, we get verified global ERA bits, which we can then use. So the cut and choose protocol requires a few tweaks as compared to the original one, because that one was built for multiplication triples, which have a linear relationship, whereas ERA bits have a non-linear relationship. This means we need some auxiliary information, and in this case, we use tiny OT triples. So the naive approach would be to generate secure triples and using a process like cut and choose and use them for ERA bits. Our approach was to instead have the party that proposes the set of tiny OT triple set of ERA bits also propose the required tiny OT triples and use them without verifying for correctness. In the paper, we analyzed this version of cut and choose and prove that this doesn't give the adversary any additional advantage. So this is the modified game, which uses unreliable triples. Each party PI proposes a set of ERA bits and the required tiny OT triples. We shuffle them using 2 public permutations. We open C ERA bits and C prime sets of tiny OT triples and verify for correctness. If any of them fail, then we abort. Otherwise, we take the remaining ones and place them into buckets. And we carry out a bucket check protocol within each bucket. We select the top ERA bit and perform a pairwise check with every other ERA bit in the bucket using the tiny OT triples. If all of the checks pass, then we output the top ERA bit as a verified private ERA bit. So analyzing this game gets us the following parameters. For 40-bit statistical security, we found that we only have to open 3 ERA bits and 3 sets of tiny OT triples if we have a bucket size of 3 and we generate ERA bits in the order of 1 million. This is analogous to the original cut and choose game for multiplication triples, where we have to open 3 multiplication triples for 40-bit security. As I mentioned, we have improvements to comparison and truncation using ERA bits. Our constructions work over signed and unsigned data types. And we've benchmarked some end-to-end applications like logistic regression and convolutional neural networks, the benchmarks for which are available in the full version of the talk. And the code is available as a part of the MP-Speeds library. So I'm just going to conclude by showing these benchmarks. Basically, if we consider the dishonest majority case with 2 parties and active corruption, then we are about 3 to 5 times better than debits if we consider the number of comparisons we can do per second, and about 5 times better if we consider the communication cost per comparison. So that was a quick overview of ERA bits. Thank you. I'm ready to take questions.
Okay, thanks, Rahul. If anyone has questions, go ahead and ask them here. In the meantime, I had a question about your last slide where you showed some empirical improvements. Yeah, improvement factor 20 to 60x. Are you just talking about the raw generation of these ADA bits, or do you have like an application in mind where the ability to switch from arithmetic to Boolean is like a killer feature?
Yeah, so 20 to 60 is considering all of our end-to-end applications, I believe, like logistic regression and the other ones we've benchmarked. It's not the generation of data bits itself.
I see. So that's the whole protocol is improved, even offline and online phases.
Yeah, I believe this is considering the total communication.
Okay. I also was wondering how the conversion from Boolean to and from arithmetic, does that affect the round complexity in the online phase?
As opposed to using debits, you mean?
Just in general, but sure, in comparison to the prior work as well.
I'm not really, I don't have the numbers off the top of my head. Maybe one of the other co-authors can answer if they're online.
Okay, in the meantime.
Yeah, do you hear me?
Yeah, go ahead, Peter. Hey.
Yeah, so the conversion in the online phase is just the same as previous works using a binary circuit. So then the round complexity depends on the depth of the circuit, unless you do it using garbled circuits to get a constant round.
Okay. Thanks. I see a question in the chat from Hao Chen. Does this work improve truncation and comparison in the semi-honest setting as well?
In the semi-honest setting, I think we're about, we've benchmarked for concrete applications, and I think we matched the performance of something like ABY3. I don't really remember the figures for semi-honest security though.
This is Marcel here. If I can say briefly, it doesn't really improve on ABY3 because that uses like very specific tricks, but it does improve as far as I know on other settings like Shamir secret sharing, because there are like not that many special tricks you can use with Shamir secret sharing.
Okay, great. And I think Antigone also has a question that she can ask.
Yeah, thanks, Mike. So which comparison protocol you're improving upon? Was it the one in ABY, or which one are you comparing against for these numbers?
The comparison protocol, the truncation and comparison, I think they come from this paper by Katrina and Sebastian, I think. So those are the ones we've implemented.
Okay, if you can paste in the chat, I don't know which one you're referring to. It would be great to. Okay, thank you.
Okay, I don't see any other questions queued up, and we're exactly at the end of time. So that's the end of the session. Thanks to all the speakers. I've seen in the other sessions everyone unmutes and claps, so we can do that. That's kind of fun. Thanks to all the speakers. Thanks to everyone for asking questions. If you haven't gotten enough MPC, then stick around in 10 minutes. The next MPC session will start, and I hope to see you all there.